Hi there, in this video we will do the returns to scale analysis of a Cobb-Douglas production function, and for that we will use the virtue of homogeneity of a given function. So let's get started. We have Cobb-Douglas production function. We know that it is specified like this. This is the parameter, alpha is also parameter, beta is also, and we have capital and labor as the two variables. So this is the basic Cobb-Douglas production function. For the sake of homogeneity test, we can introduce a scalar, which is lambda in this case, in all of the variables that are there as the independent variables. So on the left hand side and on the right hand side, we can see that lambda is introduced, and when we introduce lambda here, it should be inside this bracket because capital has a certain power, that is alpha, and labor also has a power of beta. So whatever gets introduced to labor and capital should also possess that power. Now we can separate these bases, that is lambda alpha, k alpha, and then lambda beta and L beta. So after expanding the powers, now we can gather the two lambda terms, and here they are. The two lambda terms have been gathered, and the remaining terms are left on the other side. And then we have this expression in which we have summed the powers because the bases are the same. After doing this, we can rearrange it and write it in this way that this becomes equal to the original production function, that is a k alpha L beta. So we anticipated this, and now this coefficient can be written as it is, whereas instead of this value we can write the production function, that is q. So the original production function now has been augmented by this factor once we introduce lambda on both sides. Now we focus on this power of lambda, because this power of lambda will determine that what is the degree of homogeneity, and this power is alpha plus beta. And we know by the assumptions of Cobb-Douglas production function that the sum of alpha and beta, that is the powers of capital and labor, is equal to 1. So by following that assumption of Cobb-Douglas production function, we can say that this is a linearly homogeneous production function, or it is showing linear homogeneity. But there is a caveat here, because these can be intermixed, these two terms, that is linearly homogeneous versus linear and homogeneous. Here we are simply talking about homogeneity and its degree. However, here there are two different concepts. One is the linearity of the function, other is the homogeneity of the function. Linearity is in the given function, and homogeneity is the nature of it, if it is present or not. So linearly homogeneous means that it is homogeneous of degree 1, whereas here the homogeneity can be of degree 2, 3 or any other. So this was the differentiation between these two misleading terms. Then the economic implication is there, and it means that if linear homogeneity exists, it means that all the independent variables that are actually inputs in this case, which are capital and labor respectively, if they are increased by the same proportion, and that same proportion is lambda as we introduced it, the dependent variable, which is actually output in this case, q, shall increase by same proportion. So that implies constant returns to scale, something that we have studied in our standard microeconomic theory. So it means that capital, if it becomes double, and labor, if it becomes double, the output will also become double. This is what constant returns to scale will yield. So in this case we can expect that there is constant returns to scale because the sum of these two powers is equal to 1. But there are the two possibilities as well, because the sum will not be necessarily equal to 1. It can be greater than 1, it can be less than 1 as well. So if it is greater than 1, then it would imply increasing returns to scale, and if it is less than 1, then it would show decreasing returns to scale. And definitely if it is equal to 1, it will show constant returns to scale. Here we are considering this possibility, that is constant returns to scale, whereas in other production functions there can be non-constant returns to scale or variable returns to scale, which is collectively increasing and decreasing returns to scale. Here you can see that we have a diagram in which we have the inputs on x and y axis, that is labor and capital, and we have the isoquants, that is Q1, Q2 and Q3, and these are the various isocost lines that show the various levels of budgets that the firm or the producer has. So these are the various points of tangencies showing the various equilibria that we have, and now we can see that these equilibria have joined, and if the line starts from the origin, it will pass through all these equilibria, and it will give rise to this path, which can be termed as expansion path, because it is showing that if we are increasing the labor and capital in a certain proportion, the output is also increasing in the same proportion. So that is a desirable thing for us, and it is showing that we are actually dealing with constant returns to scale. This is why we can say that it is quite relevant to our current situation of Cobb-Douglas production function. This is the expansion path of a Cobb-Douglas production function that shows a constant returns to scale. We can also do this with the help of a numerical example, and that will make the things much more easy to understand. For example, we have this numerical in which the value of capital A is 100, the value of alpha is 0.9, and consequently the value of beta is 0.1. So you can see the sum of these two is 1. Now, for the sake of homogeneity, we will introduce lambda on both sides wherever we have labor and capital. You can see that has been introduced, and we have 100, and then the brackets have been expanded. We can gather the terms that are based on lambda and the terms based on capital and labor. We can combine these two bases, and the sum of the parts will be equal to 1, that is 0.9 plus 0.1, and this will remain as it is because this is actually the actual production function. So lambda is here as a multiple, and its power is 1. So when the power is 1, it means that it is showing constant returns to scale. Economic sense is this, but from the mathematical point of view, we can say it is linearly homogeneous because it is homogeneous and with the degree 1. So this is the Cobb-Douglas production function in its standard form, in its most common assumption of constant returns to scale. But we can do further experimentation, and here we have two examples: DIY, do it yourself, 1, and it requires you to deal with this function, production function, and you can see that it is having a power of 0.9 and 0.2. So this will give you interesting findings. What you are required to do is to find out the homogeneity and then interpret the results in the light of returns to scale. This is another question that you can solve, and this is the DIY2, and again you can check the homogeneity of it, and also you can explain the economic meaning in terms of returns to scale. So in this way we have understood the returns to scale with reference to Cobb-Douglas production function numerically, diagrammatically, and with the help of its basic theory. This Cobb-Douglas production function and its returns to scale by using the homogeneity process.